Okay, in this chapter, we're actually looking at complex numbers. So, what are complex numbers? So, complex numbers are a combination of real and imaginary numbers. So, real numbers, you are all familiar with real numbers like integers, fractions, rational numbers, irrational numbers. And so, where imaginary number comes in is when you have numbers which are square root of a negative value. So use I to denominate those values which are imaginary. For example, this is a number where it's equals to 3 plus 4i. So what happens is this is the real number and 4 is the imaginary number. Okay, so let's consider for the few concepts that we will discuss later of these two complex numbers. So you have z1 equals to a plus bi, and z2 equals to c plus di. So I representing the part which is the imaginary number. So normally in most of the questions in complex numbers, you're asked to simplify a calculation. So what is meant by simplify? Let's say you have z1, for example, let's go for plus. So z1 add z2. So you're just adding a plus bi plus c plus di. And what happens here is, if notice I rearrange, so we only add up real numbers with real numbers and imaginary numbers with imaginary numbers. Okay, so multiplication, same thing, z1 times z2, so a plus bi times c plus di. So if I were to multiply a with c plus di and then bi with c plus di, okay, this is still not the finish yet. What happens, you have to also have to notice that I will actually have multiplication I times I in some cases. So what happens with the I times I? It becomes I squared, where it's equals to -1. So like in this case, bi plus di, when that is multiplied, it becomes, here you notice that it becomes negative. Okay, so there's also a concept of conjugates. So what are conjugates? Basically, it's kind of like a twin or opposite twin. So conjugate is where you actually have this a minus bi as opposed to this one. So it's a twin of this one. What happens is you only have let's say if I portion here, you will invert this sign based on this complex number here. Okay, how does a conjugate appear? For example, like when you're solving a root value of a quadratic equation, sometimes you may come up to a calculation something like this. So plus minus square root of the number. So you notice that you actually now have that number and then plus minus 3i. So these are conjugates of each other. So why do I use it? There's some cases where you actually have conjugate multiplication. So what happens is when you times itself by its own conjugate, this comes about and you get a squared minus bi squared, and you notice that I has disappeared from it, and it's quite useful in certain uses. Previously in the previous slide, I did not consider a complex number divided by another complex number. Okay, this is where we're going to look at it in this part here. Oops, sorry. So here, if you have, for example, these two conjugates multiplying each other, so you actually get minus 2 squared plus 3 squared. So for this next portion, so let's consider this vector again. So if I have division, so let's say of z2 divided by z1, so the strategy here is to use the denominators conjugate, so a minus bi. So what happens is when I multiply it by its conjugate at the bottom, so you notice that -2 doesn't change. I'm just changing the sign on the imaginary number side. So actually then I get a number in such, and you simplify further to get the real value number and also the imaginary number. So simplification actually tends to mean that you want it to get into this this form again, z plus x plus yi. Okay, so there are other rules with the conjugate. So things like this, where you have z1 plus z2, when you conjugate the whole addition of this, it's actually equivalent to conjugate of z1 plus conjugate of z2. Same goes for the multiplication part. Okay, another concept in complex numbers is the Argand diagram. So it's actually just a geometrical plot on a y and x axis. Okay, so if you have z1 equals to -4 plus 6i, you notice that it's -4, 6i, z2 is 4 and 2i. And how you can use it is kind of like a vector plot in some ways. So if you have addition, for example, of the two vectors, so z2 plus z1, so let's say if I shift z1 over to this side, so looking at it like a vector, so the net product of it would be 0 plus 8i based on the calculation method, but you can also see here that it's by drawing method, it's also, so 0 and x, it doesn't move, 1 2 3 4 5 6 7 8 in the y direction. So same goes for z2 minus z1, so the net vector will give me z2 minus z1. So you notice there's 1 2 3 4 downwards, 1 2 3 4 5 6 7 8 towards the x direction, and which is what you get based on the calculation. So in Argand diagrams, you can actually use it in a graphical way to show your addition or subtractions of your complex numbers. Okay, so another important thing in complex numbers is to represent the complex number in the polar form. So what happens is you have your x and y values, and basically, so it's a line with an angle. You can actually represent it by your polar form, which is r cos theta equals to a. So r cos theta gives me the a value based on your trigonometric functions, and r sine theta will give me my b value. And if I look at this by putting it into the function of a plus bi, so a equals to r cos theta and b equals to r sine theta, I get this function here. So this is my polar representation of my complex number. Okay, so if I'm looking at the line segment, this r, the modulus of it will give me the value. So the modulus of the complex number, so which is this r value. Okay, because cos theta squared plus sine theta squared will actually give me my oh sorry, there's an I here. I have to check whether it gives me one, but okay, now mind. Proceed with it. So there's also another thing called theta equals to argument z. So that's actually just looking at the angle here. So argument z actually looks for the angle. Okay, so notice that you actually just now represent your complex number at x plus yi. You can also actually represent a polar form. This is the shorthand for the polar form. There's also a third form, which is the exponential form. Basically, cos theta plus I sine theta, you can actually represent it by this form. And what happens is there's quite a lot of uses by putting in exponential form. Okay, but let's look at some rules first. So let's say if you have polar form, when you have multiplication, z1, z2, it's just multiplying the r values and adding up the angles. If you have division, so you actually have dividing the r values and subtracting the angles. So you can see that somehow it's actually, by having it in the polar form, it makes calculation a bit easier. So if you have roots, all you do is just root the r value, and the angle you divide it based on the root value. Okay, let's look at a few examples. So let's consider z1 and z2. So in this case, if I multiply it, it's just 6 times 2, and then the angles, I add them up. So I actually get this as the product. So division, so 6 divided by 2, and then the angles, I actually subtract. Okay, and if I have root, So you can see I root the r value and also the angle I divided by, in this case of root, just a square root, you divided by 2. Okay, I want you guys to think about it. Let's say you have this in exponential form, since you are actually familiar with logarithms and having in exponential form. Try to do the same calculations here. You will notice it actually does make sense easier with this. Okay, there's also another important website I would like you guys to look at. Try to look at this website. So it talks about the connection between these irrational numbers, which is kind of like a interesting relation in nature in some ways. Okay, so the exponential form, when I actually have it in RE I theta, okay, so what happens is just look at this one. If I have the angle here as 6 theta, for example, so all I'm just doing is replacing the angle value. So in this part of the equation, that the angle becomes 6 theta 2. Okay, so there's another concept in complex number, which is De Moivre's theorem. So if I were to have this to the power of, let's say, n, De Moivre's theorem actually just states that I would, in this case, r have to the power of n, but in the internal bracket, oh, I missed it out. I can actually just times the angle, so it will be n times theta, n times theta. Okay, let's look at this example here. So what happens is when I power it to 3, so 6 to the power of 3, and you notice that I've actually multiplied n into it. So 3 times pi over 15, 3 times pi over 15, and that becomes cos pi over 5, sine pi over 5. So De Moivre's theorem actually, in terms of if you have the power, it makes your calculation easier in having it in this form. Okay, there's also another concept where you actually have trigonometric representation using Euler's. So looking at just now the equation of ei theta equals to cos theta plus I sine theta, if I have it in this form, ei theta minus e negative I theta over 2i, I will actually get sine theta. Same goes for this, where I have ei theta plus e negative I theta over 2, I will actually get cos theta. And why is this important? I can actually then use the exponential representation to make some trigonometric calculations. For example, let's say if you have 2 sine theta cos theta, so I actually will multiply this with this component here. So I actually have this. So ei theta times ei theta, this will become e2i theta, and e negative I theta times ei theta, so this will become the whole expression here becomes 1, so negative 1 plus 1, that actually cancels out. So what remains is this, and you can see that this again has the same form as this, only thing the angle is different. Now it's 2 theta. So what happens is this is actually equivalent to sine 2 theta. Okay, for another concept in complex numbers, you want to find locus. So what locus actually means is a set of specific points that satisfy a condition. Okay, let's look at examples. So let's say my locus is defined by the magnitude z equals to 4. So what does that mean? So let's say if I were to place z into the equation, okay, and I get the magnitude of it. So what I'm actually doing is I'm actually getting a circle equation. So my locus is actually points which are along this circle equation. If I write now for this example, so my locus is defined by argument z, so means that the angle of pi over 4. What does that mean? So what happens is you have this as your r function, and then you have the angle. So what happens is the angle pi over 4 equals to y over x. So what we are getting is y over x equals to tangent pi over 4. This is tangent 45 degrees, so it's equals to 1. So what happens is you have y equals to x. So basically my locus points along this y equals to x line. Okay, this is the last part that I've included. So I find that another important thing about complex numbers by having this exponential form is you can actually add in an element for rotational or phase shift. So let's just look at the plots of this onto this diagram, let's say of n magnitude of 1. So we actually have EI pi over 4 as this line. If we have EI pi over 6, we have this line, and pi over 2 will be here. And if we have 3 pi over 2, we're actually having the line here. So what I meant to say that if let's say I have this original vector and I want to rotate it by say pi over 2, so by multiplying it, you notice that this now angle becomes pi over 6 plus pi over 2. I've actually introduced a rotation or phase shift to the equation. Okay, and then so that concludes complex numbers.